have a look at these. Okay, so we're going to rework all of these. Oops. We're going to work all of them, and we can always add a little something to the mix. So I'll just kind of go through them. So the first one, we just wanted to expand this thing to third order. So what you'll notice is it looks like these derivatives are pretty basic because there's no there's no chain rule involved. So you want to get to third order, you want f of x equals f of 0, f prime of 0 x half f double prime of 0 x squared. And then the question is, could we do the kth term as well? X to the k, then we would have the entire infinite series. So that's worth looking at. So for the homework, which is really the rework of the entire exam, plus the little added things, the homework would be to expand to all orders and see if you can get see if you can get a kth1 and a closed form for it. Sure that works, because once you do a couple of these, you're always bringing down that power. You're going to have an alternating plus and minus sign. Right, let me just remind you. So f prime was a half 1 plus x to the minus 1 half. You have 1 half minus 1 half 1 plus x minus 3 halves. And if we do the third, 1 half minus 1 half minus 3 halves, 1 plus x to the minus 5 halves. So you keep going, the next one will be 5 halves. And see if we can get that kth1 without too much trouble. You know, we'll have 2, we've got 2 to the third in the denominator. We've got -1 to a certain power. And then, but here we're going to have the, 3, 5, 7, etc. Okay. So probably can do it. So we'll do it to all orders. And something not everybody saw, the nice thing about putting a 0 in there is it's always just 1. All of these to whatever power whatsoever, right? It's just a 1. So this one lends itself to trying to get it to all powers. The pattern might not set in until the first derivative might not quite fit the pattern, but eventually you'll find a pattern. Okay, so good, that was that one. Now the second problem we could even discuss in terms of a physical application, which we didn't do for the moment, but so for the second problem, this one we could conceivably also expand to all orders. But let's look at it first. So we have f of x equals 1 over x plus 1 over 1 minus x. And we're looking at 0 less than x less than 1. So between 0 and 1, you have something. And this one here, and the 1 over 1 minus x. See, at x equals 1, it's already diverging. So what this one was would be something like this. And so the function that we were looking for is doing something like that, very roughly. Okay. It's actually a lot flatter down at the bottom. We'll see that in a moment. So this one lends itself really nicely. What you find out is x naught is equal to 1/2. So x naught is 1/2. We can go ahead and erase this. You find, and then, so what you find here so far is f of x, I believe it was, I have that here, 4 plus 16, so 4 plus 16, 1 minus, no, sorry, x minus 1/2 quantity squared. So when you have a polynomial like this, you don't want it expanded out. Again, you kind of lose the information you have here, because you can clearly see, 4 plus 16 over x minus 1/2. You see that around here you have some parabolic thing centered around the x 1/2. That's kind of the whole point of that. And so the next thing we could do is ask, can we get the kth derivative on this one? And it possibly not so bad, because we have f prime. Well, we can write it. What's the best way to write it? Some people want to write it like this: x to the minus 1, 1 minus x to the minus 1. And your f prime is minus 1 x to the minus 2 plus 1 minus x. Do it this way, plus negative 1 minus x to the negative 2. Inner derivative will be a negative 1. So this one is always going to give you that same thing. It's always going to get rid of the minus sign over here on the second one. F double prime minus 1 minus 2 x to the minus 3 plus 2 1 minus x to the minus 3. It's always going to be a plus sign here. So the kth one is going to build up an alternating minus 1 to the something here. And then you're going to get these higher powers x to the minus 3 and 1 minus that, or x to the minus k, 1 minus x to the minus k. But what you're going to have here, because this critical point is 1/2, you're always going to have a 1/2 1/2 to the minus 3, right, equals 2 to the third, etc. You're going to put those. And you're going to get the same thing on this one. It looks complicated, but it's always going to be 1 minus 1/2, right? 1 minus 1/2. So let's go ahead and try for this one. Find all orders. Looks like it's doable. I haven't done it. Up to you guys to figure it out. Looks doable. And while we're at it, what kind of a physical thing could this be? Anybody think that far ahead? So in 105A, we are talking about things like u of x. So suppose you had u of x equals k over x plus k over, now I have to have some, minus x. Suppose this were electrostatic type of problem. You could imagine you have a positive charge here, and out at A you also have a positive charge. And they're welded. This is the kind of thing you get in a physics 4A problem. They're welded to the, they're fixed to these points, and then you have a test charge anywhere in here plus Q. So that could actually be, and the thing is constrained to move, like a beam to move on the x-axis. That would actually be a potential of that form. And so you'd have these two repulsive potentials and this thing in between. And its equilibrium, if they're the same, would be right in the middle, right? And if you moved it a bit, it would oscillate back and forth. Make sense? It would oscillate back and forth, and it would essentially be oscillating back and forth in this potential well. We can put this on the 105, the next 105 exam. Don't tell me. Yeah. But yeah, so that would be an application of this kind of thing. Not even that dry. Good. Then the third problem, we can also get a little added mileage out of it. So here we were expanding in a Fourier series cosine of x over 2 from minus pi to pi. And if you look at this graph, when x is equal to pi and minus pi, the cosine of pi over 2 is 0 minus pi over 2. So this is what this function looks like. And it just looks like that. And first of all of the b sub k's are going to vanish because it's an even function. And the a sub 0, or you can even just go to a sub 0 over 2 right away because you need that. That's going to be 1 over 2 pi integral cos x over 2 dx. So you get that, and that just gives you some value. And then you can get all the a sub k's. And I gave you a tip on those. So when you have time to do this, you'll find it's not so bad. You take 1 over pi minus pi to pi cos x over 2 e to the minus, no, not e, cosine, sorry. Cosine kx dx. Even function, the trig identity I gave you makes it pretty basic, so as long as you're careful on that, I'll just put down what we end up getting. So for this one, we get cosine x over 2 is equal to 2 over pi plus sum 1 over pi minus 1 to the k plus 1, 1 over k squared minus 1/4 cos kx. Now, just for some added interest on this one, for x equals 0, of course, we just get 1. Cosine of 0 is 1. So we're going to have 1 equals 2 over pi plus this sum 1 over pi k plus 1 k squared minus 1/4. And what we want to do here, just for added interest, is get an approximation to pi again. So what we can do is multiply the whole thing by pi over 4. So we'll have pi over 4 will be equal to pi over 4, 1/2. And we do pi over 2. Now 4 is good. So the pi over 4 here does the following. We get, 4 over pi. I'll did that right there. 4 over pi gives us minus 1 to the k plus 1. Pi cancels. Then we can 4. That's going to be k plus 1. 4 k squared minus 1. Yeah, this works this way. K equals 1 to infinity. And they're a little awkward, they don't have a really thing, but if you could add like 4, 5, or 6 of these and compare it to the actual pi over 4, that would be interesting. So take, after you've done this, I've done this, make sure it's right. Take k equals, say, 4. And add a few of those fractions up. I think that'll work. And see what happens. You see what you're getting. When k is equal to 1, you've got positive here, you've got 4 minus 1, you've got a third. Right power here, 2 plus 4 is that as make sure I got the first one too. Yeah, give it a try. Give it a try. Okay, finally, this last one takes us right into where we left off before the exam, so this will be good. Okay, good. So the last problem was a Fourier transform. So just to add to the record, for an estimate of pi. We'll do it. Okay, good. Let's look at the last one here. So we have f of x was equal to, make sure we get this, cos ax e to the minus bx. Yeah, cos ax e to the minus bx. X greater than 0, x less than 0. So it's good to look at this first, and you see that you have something that's, depending on the value, g is damping out, and you have to know that the exponential damps things out very well indeed. Okay? We're going to be using this later on as what's called a converging factor. Good, and then we want the Fourier transform. Well, just set that up. So we have f at k 1 over root 2 pi. Well, I'll just put the definition for us. So minus infinity to plus infinity, f of x equals minus ikx dx. Okay. So this is a Fourier transform. For the particular function, so we have 1 over root 2 pi 0 to infinity cos ax e to the minus bx e to the minus ikx. Now this, this is interesting in its own right, but generally, or this is often used to make something vanish at infinity, okay? Because it's required for a Fourier transform that your functions vanish at plus or minus infinity. And this function always does the trick. Okay? So then I gave that tip for us to write the cosine as 1/2 e to the IAX plus e to the minus IAX dx e to the minus IKX dx. And then you're going to have two integrals, 2 root 2 pi. So what we want to do is just do e to the IA minus b minus IK x. If you do it this way, nothing can go wrong. Plus e to the minus IA minus b minus IK x. If you do this and you put parentheses around here, this is just a number and you can call it anything you want. And the integral of this is easy, you know, it's 1 over that number times e to the x, e to that argument times x. Now what happens here for the limit, not everybody saw this, for the limit, the upper bound, that e to the minus bx is there and it kills these other ones. Because they just have magnitude, if t is the product, is magnitude 1. So the e to the minus bx kills them at infinity. When you evaluate it 0, it's e to the 0 is 1. So you get a very clean result. Now, I asked for the poles, and that's something we've just started talking about, so it's something we're going to make up today. What's my best form of this thing here? Yeah, I'm going to write it down, and you guys can work towards this result. Actually, here's what I'm going to do. What we find is poles at k equals, and I think I'm going to do all this, a plus ib, k equals minus a plus ib. This is going to segue right into what we're headed for and what we've been doing. So this was my result. I'm going to show you more about how I got it because that's important. But suppose you're in the complex plane, but now k is allowed to be complex. Okay. When we started this exercise, k was real, right? K was real. So what we end up with when we do this integration here is that there is a pole at A, IB. There's a pole over here, negative A, IB. So there are two poles right here. So we had just gotten to this point. I think one of you guys made a good stab at where those poles were. So you do these integrals, here's what you're going to get. And this is the form that we're looking for here and henceforth. Okay. So I'll put this in the bottom instead of that. Okay. So the result will be 2's cancel. Result will be 1 over root 2 pi, cancel that 2 already. In the numerator, I have negative IK up here for now. So what we mean by poles is that those are the places where this denominator vanishes, right? And you have two of them. And yeah, this algebra will get you here in it's only a couple steps, it's not bad at all, but you'll get to this form here, you can pull out negative I if you want. What's parentheses around here? This is what I got, make sure you get the same thing. So the significance of this is that this thing, this f hat of k is thought to exist in the entire complex plane. Right? Even though when we started, we were thinking, yeah, k is, we wanted to do this integral, it was well defined, okay? And we thought, okay, k is real, we know b was real, x is real, right? But k is actually in the entire complex plane, and f hat of k in particular. So we have to make contact with where we were before the exam. So I want to leave this up here. This is good. And I'll put here resolve Cauchy integration. I'll just call it Cauchy integration for the moment. I was thinking of putting one of those on the exam, I realized that was premature. But this problem was actually not premature, it was right perfectly placed. So remember we had this f of z dz equals 0 if you've got some closed curve in the complex plane. Okay, and then we said f is analytic in and on z. And then we had, next thing we had was if we were circling some singularity, and that was exactly what these guys are. So we had a singularity here, and we said, okay, we'll just go around here counterclockwise. We'll loop around this thing, and now this theorem is still satisfied. And then the third step was when we did dx over x squared plus 1 minus infinity plus infinity. And that's kind of, I'll put a question mark here. That was kind of where we had left the topic, where we're going to pick up again. Okay. So yeah, we had this theorem about complex integration contours, circling little infinities, and then we had this problem. Anybody remember what happened on this one here? It's all haze. Well, yeah, it's because we've been thinking about other things. So this is what we're going to pick up again. How about you guys? Remember this? Integral vaguely. Because what I'm going to do is relate, notwithstanding that those are x's and these are k's here, I'm going to relate it to this thing right here. So the way we solve this, and now I need more boards, so let's see what, yeah, I can get rid of this. I'm going to practice a bunch of these. I'll put at least one up next week. By the way, for the recitation next week, all these problems from the exam will be perfect, right? We'll have it prepared, we can knock it out and make sure everything's cleared up. Okay, so we got to this problem here, and here's how we did it. We need a good sized picture now. So we have the x-axis and this function f of x equals 1 over x squared plus 1. Well, this function just looks like this. And it's an infinite integral, and we want to get the integration. The whole thing turns out to equal pi or something, okay? is consider integral dz. I don't have to rename that integral, it could still be x, but dz z squared plus 1 equals integral dz, and then we get this factorization, z plus I times z minus I. And when we do this, we are in the complex plane for sure, okay? Oh, it sucks. And so when I sketch this situation here, it's not this graph. It's not this one I'm looking at above here, but rather this is just in the complex plane. And the integral I'm trying to get is from minus r to r. And then I'm going to integrate from minus r to r and let r go to infinity. That would be my real integral that I was looking for. What I'm going to do instead is use the Cauchy formula. Minus r to r, swing up here. And what I have an I is a pole. Okay. I have a pole at z equals I. So I'm going around the pole, that means I'm using this theorem here. And that's in your notes, and we're going to repeat this because this is the all-time important example. So what we did was we showed that as r goes to infinity, this semicircular integral of this thing vanishes. This goes to 0. The one that circles the pole goes to 2 pi I, essentially, 7 times 2 pi I. And the combination of the two gives us this one here. In other words, this one here plus the semicircle is 2 pi I f of the thing inside. So that's the technique we're going to use again and again. Right now I'm just sketching it because we've done this before, but I want to bring it into the context of this one. So this thing here is a significant Fourier transform of a cosine, basically, a damped cosine. And its result lives in the complex plane, and it has these two poles here. And the way we're going to treat this in future is we will also, like, suppose we wanted to integrate this Fourier transform and get the original function back. We would do the same thing here in the k plane. Here it's x through z, here it's k, but it's the same scenario. We would be circling, actually here it's more, we have to circle both poles. Okay. This one over here also has a pole at negative I. We're not circling that pole, so it plays no role, has no contribution. Okay, so that was the significance of this problem here. It's looking forward to stuff that we're going to do. Let me say a little bit more about it, and then we're going to return to this problem over here. Yeah, so I need some room here. So this, like that, okay, I can erase these for now. So this was the Fourier transform of f of x equals cosine ax e to the minus bx, right? For x greater than or equal to x greater than equal to 0. You'll notice if I had wanted the Fourier transform of the cosine, I would have had problems. Because cosine doesn't vanish at infinity, right? It just oscillates. But this trick here, I can make b arbitrarily small, and that thing is still forcing the function to vanish at infinity. So if I take the limit as b goes to 0 in some subsequent calculation, that will give me the Fourier transform of a function that doesn't actually converge, right? So that's an important technique as well. So in that sense, this is what's called a converging factor. You have some function that isn't vanishing, but it's not diverging either. At vanishing infinity, if you can get the Fourier transform of this thing, in your final result, you can, under some circumstances, take b equals 0 and have a good result. So there's a lot of physics going on here. But yeah, for the moment, this exam problem and current homework problem is to work your way through, get this thing, and then locate the poles in the complex plane like I did here. And then realize that this is the kind of object we'll be going back in and creating. We're going to solve differential equations with this technique. So let's return to this one and get up to speed on that. And let me just put down the Cauchy, both of those formulas. We also have the Cauchy integral formula. I'll put those both up there. Okay, so when I erase all this, start anew. Yeah, okay, everybody's got that. Okay. So integral f of z from c equals 0, comma, if f is analytic in and on the contour C, which is some closed loop. Okay. Positive orientation down one west. That's the first thing. Next thing is we apply that to a multiply connected domain. So apply to multiply connected domain. Multiply connected region. Then we have, I'll write it down and I'll draw a picture. C plus C1 f of z dz equals integral f of z dz c plus integral f of z dz c1 equals 0. So now the multiply connected region, this was just one hole in it. C was the outside, but at some point you had to go in here. You had to go in here, go around clockwise, and lead along the same path you came in. So this one here is clockwise. But if I do this one counterclockwise, then I pick up a minus sign and I send this over to the right side and I get f of z dz around the outside equals f of z dz. I'm going to write minus c1. But this minus C1 is the proper positive orientation. So what you've done is you've replaced the integral around this one here with the integral around the center, around that little point. Okay. So from here, we get Cauchy's integral formula. As a direct consequence of this right here you have, so I'll put this down as Cauchy's integral formula. And f of z is analytic and on C and again, this is now a different function, okay? Because f of z minus z naught bc is equal to f of z naught inside, and it's equal to 0 if z naught is outside. So this is the one we can use again and again. So now, in terms of this second scenario, we've explicitly pulled out a pole, okay? Taken a function that satisfied this, and we've definitely installed a pole right there at z sub 0, because we multiplied it by 1 over z minus z sub 0. But this one goes back to this one here, so the Cauchy integral theorem is one you're going to use all the time. So now that when we have this, which came directly from here, we want to be able to do that 1 over z squared plus 1, and then I'll add a couple to the mix. Okay. And the orientation aspect is good too. So you know what? I think I'll assign this one. I'm going to work it most of the way, but I'll assign that so that we really get it. Okay. So the one I just had on the board, and we're going to use this theorem right here. And if I do this closed integral in this form, counterclockwise, a positive orientation. So let's return to this thing here. Once we've done this basic one, the kind that came on the exam problem, with a lot more constants, it won't be bad. Once we get this one dialed in, no problem. Okay. So we have, once again, f of z, or I can identify that first. So we want to get to use that formula here. So we start with our dz z squared plus 1. Okay. That's the integral we're looking for. And the path is along here. So what we have is, for integral dz z plus I z minus I. So that's that factorization. And we have the poles at I and minus I. So what we could do is we could say that is 1 over z plus I, just dz over z plus I, times 1 over z minus I. See, so that's the z sub 0 is I, and f of z is 1 over z plus I. Let me write it so that it looks exactly like this formula over here. So I would have 1 over z plus I that's the way it looks. And apparently, that's going to be 2 pi I f of z sub 0. So is that going to be equal to 2 pi I f of z sub 0 equals 2 pi I, so I'm just comparing it to this formula here, 2 pi I 1 over 2 I, because z sub 0 is equal to I, right? 1 over 2 I is equal to I. So this is a fantastic and really useful thing here. So I may have even put that other problem up there.
So what's the problem here?
Yeah, so homework. What about the other pole? What about the pole at minus I? I think this is one thing we all have to do, have done before. So if you want to use Cauchy's integral theorem for the pole at minus I, this is the integral we're looking for, right? We have to close the contour at the bottom half plane. So when you close it in the bottom half plane, you now have a clockwise integral, that gets a minus sign. But the other sign, so yeah, make sure you go around, do it around the bottom half plane, and then make sure you get the same integral when all is said and done. And I'll put one more note here. Why does the integral dz z squared plus 1 go to 0 as r goes to infinity? That was Darboux inequality. We had done one of those before. So I'm going to put that in here as well. Yeah, this is also homework. Inequality. One more and will actually be pretty good for next week. This may have also been on the previous notes, but catching up to them. Suppose we had integral dx over x squared plus 1, x squared plus 4. Minus infinity to plus infinity. We want to use this Cauchy's integral theorem techniques. We want to use contour integration. So this time we have to locate the poles. That's the whole necessity here. So dx, we have x plus I, x minus I, x plus 2I, x minus 2I. And the first thing we do is we have a look in the complex plane, and we have I and negative I. And we have 2I and negative 2I. So there are 4 poles. And we're going to use the multiply connect version of Cauchy's theorem, of the original one really. So here we have to circle these 2 poles. And each each time we circle one of these poles, you know, so we have two poles here. The calculation would have been to do this, right, to circle these two.
I think you may have assigned this exact problem last week.
Exactly, but I could tell it was not in your memory anymore. So this is on the, did we turn this one in yet? No.
We
I
would
think
have
that's
turned
for
it in
this
last
week.
week. We would have turned it in last week.
I'll have a look,
You haven't designed any homework this week except for the stuff today.
except for the stuff today.
I'm pretty sure that question was for this week.
Yeah, I think it was for this week.
Yeah.
Cause we had the exam coming up, I don't think we were.
I think you assigned that one on Monday.
Well, for this class. it would
Tuesday.
have been-
But definitely we're gonna talk about this one.
I think we did this one.
Yeah. No, but having these under our belt will, you know, get us a long way, so we definitely wanna know these. So yeah, we're picking up these two contours, and again, we have to prove that this one, as R goes to infinity, vanishes. But this one's gonna vanish even better than the other one, so to speak, because it all comes down to having enough powers here in the denominator. So you have to have at least two, like we do over here. And when you have four, it vanishes all unfortunately, so there's no problem there. So yeah, have a look at the Darboux inequality again. We're gonna do, yeah, I'm gonna leave it at this for today. We're gonna do, there are cases where we have a stronger inequality that we can do next time. But for now, these will get us through there. You know, you can construct problems like this to your heart's content. But these two are good for what we're doing here. So if you really understand these, this one here and then this added one, we'll be in shape for what's to come. Yeah, like I said, eventually we're gonna do the kind that were on that exam. Right? We're gonna do those kind of problems and use them to solve differential equations. So a lot of stuff gets done by wandering off into the complex plane and extending your functions into the complex plane. So this is how it's done. Good, that's all I've got for you today. And next week for the recitation, we'll just start working on these